Can you hear me? Very good. All right, it's a real pleasure to be here. I attended this winter school many times when I was a graduate student. I've never experimented with this system here, so bear with me if it takes a little while to get used to. So what I would like to talk about in this series of lectures is some joint work with Dennis Gates-Gorey on conjecture of André Weil about Tamagawa numbers. So the story that I'm going to tell is an example of using ideas that come from algebraic topology to attack a question that originated in number theory. So that's what I'm going to get at eventually, but in this lecture I would just like to talk about that question in number theory and where it came from. And I'd like to start by saying a few words about quadratic forms. So by a quadratic form, I just mean a quadratic polynomial in some number of variables. So here are some examples of quadratic forms in two variables. And one of the most basic... Yes. Let me try a different pen. All right. So here are some examples of quadratic forms in two variables. And one of the most basic questions that you can ask about quadratic forms is whether or not they are equivalent, meaning can you get from one to another by making a linear change of variables? And before you can answer that question, you have to decide what ring you're working over. So the quadratic forms that I wrote up there use coefficients which are integers. The only coefficients are plus or minus 1. So I can think about these quadratic forms living over any ring that I like. Now, if I think of these quadratic forms over the complex numbers, they're all equivalent to each other because I can trade an x squared for a minus x squared by multiplying x by a square root of -1. But if I think of these as quadratic forms over the real numbers, they're not equivalent. The one on the left, x squared plus y squared, is a positive definite quadratic form. It takes only non-negative values. The one on the right is a negative definite quadratic form. It takes only non-positive values. And the one in the middle is an indefinite quadratic form, which takes both positive and negative values. So these quadratic forms are not equivalent over the real numbers, and in particular, they're not equivalent over the integers. So let me give another example. Let's say x squared plus y squared and x squared plus 3y squared. So here are some examples of quadratic forms, again, over the integers. And over the real numbers, these quadratic forms are equivalent because you have a square root of 3. But over the integers, they're not equivalent. And one way to see that is to see what happens when you reduce mod 3. So when you reduce the quadratic form on the right, mod 3, you get to ignore the 3y squared. And it becomes a degenerate quadratic form. It depends on only one of the two variables. But the one on the left is non-degenerate when reduced mod 3, and therefore these cannot be equivalent over the integers. So what I've just described to you are two methods that you might use to try to tell quadratic forms apart when they have integer coefficients. So one is to see what they look like over the real numbers. Quadratic forms over the real numbers are easy to classify. You can always diagonalize them and put them in a standard form which just looks like a sum of squares minus another sum of squares. And the only question is, how many plus signs do you see and how many minus signs do you see? In other words, what is the signature of the quadratic form? And another thing that you might do is, if you have a quadratic form over the integers, see what happens when you reduce mod 3 or mod 4 or mod 5. And the question that I would like to talk about starts with the issue of whether or not these are the only two methods that you would need to tell quadratic forms apart over the integers. So to make that precise, let me introduce a bit of terminology. So definition. So let's say you have quadratic forms q and q prime. That doesn't look right. So let's say q and q prime are quadratic forms, and implicitly I'm always going to assume that they have the same number of variables. Let's say, and I'm also going to assume, I won't mention this henceforth, but all of my quadratic forms are going to be positive definite unless otherwise specified. So quadratic forms Q and Q prime are in the same genus, or of the same genus. If they are equivalent mod n. For every positive integer n. So they're in the same genus if you can't tell them apart via the strategies that I described earlier. You can't tell them apart over the real numbers because they're both positive definite, and you can't tell them apart mod n for any n. And so you can then ask, given two quadratic forms in the same genus, do they have to be equivalent to one another over the integers? And as you might guess, from the fact that I introduced this terminology, the answer turns out to be no, but almost. If you fix a quadratic form Q and ask, up to equivalence, how many quadratic forms are there in the genus of Q? The answer is there's only finitely many, and in fact, there's even a formula that you can write down for how many there are, and that's called the Smith-Minkowski-Siegel mass formula. And before I can state that, I need to introduce a little bit of terminology. So first, some notation. So let Q be a quadratic form over the integers, and let R be a commutative ring. I'm going to write OQ of R for the orthogonal group of Q over R. So what this means is it's the set of all n by n matrices, where n is the number of variables, that preserve the quadratic form Q. So let me write that as Q composed with A is equal to Q. So an example would be to take OQ of the real numbers. So Q, here I'm assuming, is a positive definite quadratic form. So OQ of the real numbers is an object which we're all familiar with. It's the usual orthogonal group consisting of rotations and reflections in Euclidean space. So in particular, it's a compact Lie group of dimension, n squared minus n over 2. So you can think of that as maybe something big or maybe as something small, but inside it there's something smaller because Q is defined over the integers. There's OQ of Z. So this is actually a finite group. This is the group of rotations and reflections in Euclidean space that preserve a particular lattice. It's a discrete subgroup of the compact Lie group OQ of R, and therefore it's finite. And now I can make a definition. The mass of Q is the following sum. I take all Q prime in the same genus, and I take 1 over the size of this finite group, OQ prime of Z. So this sum is, if you were to ignore the denominators here, this is counting the number of quadratic forms in the genus of Q. So maybe I should make clear, there's one term in this sum for every equivalence class of quadratic forms in the genus of Q. And so if you ignore the denominators, that's just the number of equivalence classes within a genus. But these denominators are counting your equivalence classes with some kind of multiplicity given by 1 over the size of the symmetry group of the quadratic form Q prime. And that's a very natural way to count objects in the presence of symmetry. So is that visible? Yeah. Sorry about that. So the mass formula, as the terminology suggests, is a formula for this mass. So what does it say? Well, it says that the mass of Q is equal to something else. And that something else, in general, is a little bit complicated to describe. So if you want it stated in the full generality, you can look at the notes for this lecture. But let me just state it for you in the simplest case, because the simplest case is already very interesting. So to describe the simplest case, I need a little bit of terminology. So let me put this over here for a minute. So definition. A quadratic form Q is said to be unimodular if it is non-degenerate mod P. For all prime numbers P. This is, again, a quadratic form with integer coefficients. So let me warn you, this is actually a very strong condition. So none of the quadratic forms that I described earlier are unimodular. So you might think that something like x squared plus y squared is about as nice a quadratic form as you could possibly write down, but not mod 2, because mod 2, you can rewrite that as x plus y squared. And that's a degenerate quadratic form. So actually, you can show that a positive definite quadratic form, which is unimodular, exists only if the number of variables is divisible by 8. So the simplest example that you could write down would have to use at least 8 variables. Now, unimodular quadratic forms, it's clear from the definition that if I give you 2 quadratic forms Q and Q prime that are in the same genus, then Q is unimodular if and only if Q prime is unimodular, because they look the same mod P for every P. What's not so obvious, but nonetheless true, is the converse of that. That if you fix the number of variables, unimodular quadratic forms form a genus. Any 2 unimodular quadratic forms are actually in the same genus as one another. And that unimodular genus is in some sense the simplest genus. And let me just state for you what the mass formula says in that case. Going back here, the unimodular case of the mass formula says, well, I'm going to, so here n is going to denote the number of variables, and that's going to be a multiple of 8. And I'm going to take Q to be any unimodular quadratic form, so then the mass of Q is just the sum over all Q prime unimodular of that fraction I mentioned earlier, 1 over the size of that finite group, OQ prime of Z. And the mass formula says, in this case, that what this is equal to is, well, it's a fraction. There's lots of ways to write this, but in the numerator, there's some special values of the Riemann zeta function. Zeta of 2 times zeta of 4 times dot, 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 times zeta of n minus 2, and an extra factor of zeta n over 2. Oh, sorry. I'll write it over here. And in the denominator, some terms which are the volumes of spheres. So a volume of the one sphere, which is the circle, volume of the 2 sphere, times dot, 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 times the volume of the n minus 1 sphere. So let me just write this out in a couple of examples to give you a feeling for what it's saying. So the simplest example, as I mentioned earlier, is where the number of variables is equal to 8. So what happens if you have 8 variables? Well, the right-hand side is something that you can evaluate. If you know something about special values of the Riemann zeta function and volumes of spheres, and maybe it's not obvious from the way I wrote it, but it turns out to be a rational number. So the numerator and denominator are not individually rational numbers. Both of them involve some powers of pi, but those powers of pi cancel. And what you're left with is 1 over 2 to the 14th times 3 to the 5th times 5 squared times 7. And if you are a fan of exceptional Lie groups, you might recognize this number that appears in the denominator. It's actually the order of a certain finite group. It's the order of the Weil group of E8, the largest exceptional Lie group. And in particular, it appears as the symmetries of a certain quadratic form over the integers, namely the quadratic form associated to the root lattice of E8. So this fraction is actually one of the terms which appears in this sum on the left-hand side. And therefore, what the mass formula is telling you in this case is that there can't be any other terms that appear on the left-hand side. So the mass formula is equivalent in this case to the statement that there exists a unique unimodular quadratic form in 8 variables. That quadratic form is the E8 lattice. So this example might mislead you to think that the equality appearing in the mass formula is an equality between two numbers that are very small. So let me disabuse you of this. Consider another example. You could take n to be 32. And if n is 32, well, again, the right-hand side is something that you can work out. It's complicated, but it's approximately 40 million. It's a rational number. I won't say exactly what it is. But what is the mass formula telling you in this case? Well, if the right-hand side and the left-hand side have to be equal, the left-hand side is a sum of a bunch of numbers, each of which is less than or equal to 1. And if you're going to get 40 million as a sum like that, you have to use a lot of terms. So the mass formula in this case implies that there exist millions and millions of inequivalent unimodular quadratic forms in 32 variables. So unimodular quadratic forms are actually classified. In 8 variables, there's just 1. In 16 variables, there's 2 up to equivalence. In 24 variables, famously, there's 24 up to equivalence. And in 32 variables, there's no classification and no hope of ever having a classification because there's just way too many of them. Okay, so what I would like to do now with the rest of this lecture is tell you about a reformulation of the Smith-Minkowski-Siegel mass formula following ideas of Tamagawa and Wei. And the way I'd like to get there is by trying to do something that we're not going to be able to do, namely trying to prove that two quadratic forms in the same genus must be equivalent. So let's suppose that Q and Q prime are in the same genus. So what does that mean? So here Q and Q prime are, as always, quadratic forms over the integers, positive definite, in the same number of variables. So to say that they're in the same genus, by definition, means that I can always write Q as Q prime composed with A sub n for some A sub n in GL little n of Z mod n. So here capital N is some positive integer, and little n denotes the number of variables. So when I reduce mod capital N for any n, these quadratic forms I can convert one to the other by a linear change of coordinate. Now that linear change of coordinate might depend on capital N, but an easy argument will tell you that you can choose all of these matrices A sub n to be compatible with one another. So that, for example, if you take A9 and reduce mod 3, you get A3. And that follows from a compactness argument because there's only finitely many choices for what each AN can be. So without loss of generality, these are all compatible, meaning that if I take the system consisting of all the A sub n's, this is something I can think of as a single matrix A living in GLN of the ring Z hat, where Z hat is the ring of profinite integers. So it's the inverse limit of the Z mod nz's, or, well, there are many ways to describe this ring, and another is that it's the product over all prime numbers p of the ring of p-adic integers. And then what I learned then is that Q and Q prime are also equivalent as quadratic forms over the ring Z hat. So this implies, in particular, that Q and Q prime are equivalent over ZP for all P. And therefore, they're also equivalent over QP for all prime numbers P, where here QP is the field of p-adic rational numbers that I get from ZP by inverting P. And now I want to invoke something, which is not at all obvious. It's one of the main theorems in the arithmetic of quadratic forms, which is what's called the Hasse-Minkowski theorem. So the Hasse-Minkowski theorem asserts that over the rational numbers, two quadratic forms Q and Q prime are equivalent if and only if they're equivalent locally everywhere, meaning they become equivalent after over all the completions of the rational numbers. So that includes the usual Archimedean completion, the real numbers, and also all of the p-adic completions, QP, where P is a prime number. So here we're in a situation where Q and Q prime are equivalent over each QP, and they're also equivalent over the real numbers because I said all my quadratic forms are positive definite. So the Hasse-Minkowski theorem will tell me that they're therefore equivalent over the rational numbers too, which means that I can write Q as Q prime composed with B, where now B is a matrix that lives in GLN, the rational numbers. Okay, now I'm in a situation where I have two different linear transformations that convert Q into Q prime. And in that situation, I can produce a linear transformation that preserves the quadratic form Q. Namely, let's write Q. It's Q prime composed with A, but Q prime is Q composed with B inverse. So this is Q prime, Q composed with B inverse composed with A. So what does this mean? Well, in terms of our earlier notation, it means that B inverse composed with A lives in the orthogonal group of Q. But now we should be a little bit careful here because A and B are different kinds of matrices. A is a matrix with coefficients in this ring Z hat, and B is a matrix with rational coefficients. And if I want to multiply them, well, I can do that, but I have to multiply them as matrices with entries in some bigger ring. So let me introduce that ring up here. I'm going to write it as A thin. It's the ring of finite adels. So this is what you get when you take Z hat and tensor it with the rational numbers. And this ring also has a description. If you think of Z hat as the product of the p-adic numbers for all primes P, A thin is roughly the product of the p-adic rational numbers for all primes P. But it's not the entire Cartesian product. It's what's called the restricted product, where you're only allowed to have denominators at finitely many primes. So it sits inside the product over all primes P of QP. And this B inverse composed with A, it makes sense as a matrix whose entries lie in this ring of finite adels. So how did we get this matrix? Well, we extracted it by making a couple of choices. So first, I used the fact that Q and Q prime were equivalent over Z hat to choose the matrix A. And the matrix A was not unique. It's ambiguous up to right multiplication by anything in GLN Z hat that preserves the quadratic form Q. And therefore, this composition B inverse composed with A is ambiguous up to multiplication on the right by any element of OQ of Z hat. And similarly, B was not uniquely determined. It's ambiguous up to multiplication on the right by anything in OQ of the rational numbers, which means that this composition here is ambiguous up to left multiplication by OQ of the rationals. But if I think of B inverse composed with A as representing a double coset, something in this double quotient here, it's now independent of all the choices that I've made. It depends only on the quadratic forms Q and Q prime that I started with. Now, what would it mean to get the identity double coset here? So what that would mean is that it's possible to arrange my choices of A and B so that B inverse composed with A is the identity matrix. So what would that mean? Well, A priori has its matrix entries in the ring Z hat, and B a priori has its matrix entries in Q. And if A and B were the same, then all of those matrix entries would have to lie in the intersection of Q and Z hat. That intersection formed inside this ring of finite adels, but it's not hard to convince yourself that that intersection is just the usual ring of integers. So if you get the identity double coset here, it means that A and B are the same and they have integer coefficients, which is what we started with. I started out wanting to prove that Q and Q prime were actually equivalent. Well, that's what would happen if you got the identity double coset here, but in general, you need not. And if you elaborate on the argument that I just sketched for you, what you find is that this collection of double cosets is exactly in bijection with the collection of all quadratic form equivalence classes of quadratic forms in the genus of Q. So I've explained to you how to take a quadratic form Q prime in the genus of Q and extract a double coset from it. I'll leave it to you as an exercise, if you haven't seen this before, to try to go the other way. And actually going the other way, that's the easy direction to go, because what I've explained is the hard direction because it uses the Hasse-Minkowski theorem. But this collection of double cosets, well, if you're interested in the problem of counting the number of quadratic forms in the genus of Q, essentially what you want to do is to count the number of double cosets. Want to count the size of this set. Okay, so now I would like to make a slight modification to this problem. So I've defined here the ring of finite adels. It's the product, restricted product of all the p-adic completions of Q. I would like instead to work with the ring of all adels. I'll denote that just by A. So that's what you get when you also include the Archimedean completion of Q. So it's the ring of finite adels cross R. And instead of working with the finite adels, I would like to work with the ring of all adels. So I'd like to just erase this superscript up here. Of course, if I just did that, that would change the problem dramatically. But it would change the group in the middle by a factor of OQ of the real numbers, which, remember, is this compact Lie group of rotations and reflections in Euclidean space. But I'm just going to cancel that by also modifying the right-hand side. On the right, I'm going to mod out by OQ of Z hat cross R. And with those two modifications, they cancel, and the collection of double cosets is the same. This is the same set that we want to count the size of. Okay, so why did I want to make that maneuver? Well, this ring of adels has a natural topology, which makes it into a locally compact ring. And inside that locally compact ring, the rational number sits as a discrete subring. And now, this induces for you a topology on OQ of the adels. This has the structure of a locally compact group. OQ of the rational numbers sits inside there as a discrete subgroup. And OQ of Z hat cross R sits inside as a compact open subgroup. So I would like to take advantage of this using tools that are provided by the theory of locally compact groups. So one general statement that you can make is that any locally compact group has a Haar measure, meaning a measure which is invariant under left translation. And for this particular locally compact group, it's also invariant under right translation. So let's fix such a measure mu. And now because mu is invariant under left translation, it descends to a measure on the quotient OQ of the Adels mod OQ of the rational numbers. So this quotient space also has a measure on it, which I'll, by abuse of notation, just also call mu. And now what we're interested in doing is understanding the number of orbits on this space for the group OQ of z hat cross r, which is acting by right multiplication. And so we want to know the number of orbits. And well, here's a rough guess for the number of orbits. The number of orbits should be the measure of the thing that's being acted on, OQ of the Adels, mod OQ of the rational numbers, divided by the measure of the group that's acting on it, OQ of z hat cross r. Now this is not quite right. This is what you would expect if this group was acting freely. But it doesn't act freely, and so what you get from this ratio here is not the number of orbits, but it's actually the number of orbits counted with multiplicity, where each orbit you count with multiplicity equal to 1 over the size of the stabilizer group, 1 over the size of the subgroup, which fixes some point belonging to that orbit. And well, I've told you that the orbits here are in one-to-one correspondence with quadratic forms in the genus of Q, and those stabilizer groups actually correspond to the symmetry groups of those quadratic forms. So what you actually get, if you do this more carefully, is that ratio is what I called earlier the mass of Q. And so this analysis writes for you the mass of Q as some ratio of adelic volumes. It's the measure of something divided by the measure of something else. Now, if this Haar measure mu is not uniquely determined. Haar measure on a locally compact group is only well-defined up to scalar multiplication. That's fine in this case because we are, this measure mu appears both in the numerator and the denominator of this expression. So if you multiply mu by something, you won't change what that ratio is. But the next ingredient in the story is that if you make a slight modification here, you can actually canonically normalize Haar measure. And for that normalization, it makes sense to evaluate the numerator and denominator independently of one another. So for this, I need a little change of notation, or, well, I define for you the orthogonal group of R. Inside that, there's a subgroup called the special orthogonal group of R. So this is the collection of all n by n matrices such that, first of all, they preserve the quadratic form Q, and also the determinant of A is equal to 1. Now, you can take, just as before, you can look at SOQ of the Adels. This inherits a topology, and it admits a Haar measure. Let me call that mu prime to not confuse it with the Haar measure mu that I mentioned earlier. And then you can do sort of the same thing here. You could take the measure of SOQ of the Adels, mod SOQ of the rational numbers, and divide it by the measure of the compact group, which is SOQ of z hat cross r. And well, this is not quite the same expression that's appearing in our analysis before, where you had the orthogonal group, but it's not too different. And in fact, this ratio that involving mu prime is just a certain power of 2 times the analogous ratio involving mu. So up to some factor of 2, this is the mass of the quadratic form Q. So I would like to sort of ignore that factor of 2 and just focus on trying to evaluate the fraction which appears on the right-hand side here. And the reason that I want to trade the orthogonal group for the special orthogonal group is that now there's actually a canonical way to choose a Haar measure. So SOQ of the Adels has a canonical Haar measure, which was originally introduced by Tamagawa and is named after him, called Tamagawa measure. So let me sketch for you how Tamagawa measure is defined. So what does SOQ of the Adels look like? Well, it essentially factors as a product, where you have SOQ of the real numbers times a product over all primes p of SOQ of the p-adic numbers. It's not quite the full Cartesian product. It's what's, again, called the restricted Cartesian product, where you're only allowed to have denominators for finitely many primes. But let's first look at SOQ of R. That's a familiar group. That's, again, the group of rotations in Euclidean space. It's a compact Lie group. In particular, it's a smooth manifold. Now, if you want to write down a measure on a smooth manifold, one way to do that is to take a differential form whose degree is equal to the dimension of the manifold. And in this case, we want to get a translation invariant measure. And in order to do that, you can take any differential form of top degree, which is also translation invariant. So let me write V sub R to be the space of translation invariant. Differential forms of top degree on this smooth manifold SOQR. So this is a vector space over the real numbers, and it's one-dimensional. It doesn't have a canonical generator, but any choice of non-zero element in this one-dimensional vector space determines for you a left invariant measure on SOQ of the real numbers. Okay, so that doesn't help very much because, well, Haar measure was unique up to multiplying by a positive real number, and now Haar measure is coming from a choice which is unique up to multiplying by an arbitrary non-zero real number. But I want to take advantage of the fact that SOQ of R is not just any compact Lie group. It comes to you as a linear algebraic group. It comes to you as the subset of GLN consisting of n by n matrices that satisfy certain polynomial conditions. They have to have determinant 1 and preserve the quadratic form Q. So it's actually an example of a linear algebraic group, and it's a linear algebraic group which is defined not just over the real numbers, but over the rational numbers. If you write the polynomial conditions to be an element of this group, you only need rational coefficients in those polynomials. So instead of talking about differential forms in the world of smooth manifolds, you can instead talk about differential forms in the world of algebraic geometry, and you can do your algebraic geometry over the rational numbers. And what you find is that inside V sub R, you have this space which I'll call V sub Q, which is the space of translation invariant, and I'll just call them algebraic top forms on the algebraic group, which I'll call SOQ. So this is a one-dimensional vector space, but now one-dimensional over the rational numbers. And any non-zero element of V sub Q can be thought of as a non-zero element of V sub R, and therefore it gives you a Haar measure on this group SOQ of R. Okay, so that's what I want to say about the real place. Now let's talk about the p-adic places. So let's talk about these groups SOQ of QP, where p is some prime number. So these are not Lie groups in the usual sense, but there's a replacement notion. These are examples of p-adic analytic Lie groups. And this story about differential forms has a counterpart in the p-adic analytic setting. There's a notion of left invariant differential form of top degree on SOQ-QP, and any non-zero choice of such a form determines for you a Haar measure on SOQ-QP. And the collection of these left invariant differential forms forms a one-dimensional vector space, but now not over the real numbers, instead it's over this field QP. So this is the space of translation invariant top forms on SOQ of QP. And there's a similar story here. SOQ-QP is not just any p-adic analytic Lie group. It's one that comes to you as an algebraic group. It comes to you as the set of n by n matrices that are solutions to certain polynomial equations. And those polynomial equations are the same ones that we met earlier. It comes to you from this algebraic group SOQ, which is defined over the rational numbers. That means that any algebraic differential form on the group SOQ determines for you a p-adic analytic differential form on this SOQ of QP. In other words, this one-dimensional vector space VQP over the p-adic numbers contains inside it a copy of this vector space VQ that I mentioned earlier. So the upshot of this is that if I was to choose an element of this vector space VQ, let me call it omega, it's any non-zero element, it determines for you not just a measure on the Lie group SOQ of R, it determines a measure there, which I'll write as mu of omega comma R, but it also determines for you a measure on each of these p-adic groups, SOQ of QP, which I'll denote by mu of omega comma QP. And now the idea of Tamagawa measure is, let me write mu tom for Tamagawa measure. And roughly speaking, the idea is you take a product of these mu omega comma QPs for all prime numbers P and mu of omega comma R. You pick a non-zero element in this vector space VQ, and it determines for you a measure on each factor, and you just multiply all those measures together. Now, for this to make sense, there's some things you have to check, right? I'm trying to define something, this Tamagawa measure by an infinite product procedure. Some kind of infinite product has to converge. And that's why I wanted to trade the orthogonal group for the special orthogonal group. If I did this for the orthogonal group, the product that I would write down here would not be convergent. Another thing that you might worry about is, I said that this was canonical, but the definition involved a choice. It involved choosing a non-zero element of this vector space VQ. So let's see what would happen if we made a different choice. So what would happen if you took your omega and multiplied it by -5? So first, what would happen to this factor mu omega comma R? Well, if you take a differential form on a manifold and multiply it by -5, then the measure it defines gets multiplied by a factor of the absolute value of -5. So that measure would get 5 times bigger. Now, what about these other factors, these p-adic factors? Well, the story there is the same. The only difference is that you don't use the usual absolute value of -5. You have to use the p-adic absolute value of -5, which means that for almost all primes p, nothing would change. The only exception is when p is equal to 5. And in that case, your measure will get multiplied by the p-adic absolute, or the 5-adic absolute value of -5, which is 1/5. So that measure will get 5 times smaller. Once you multiply everything together, it turns out that Tamagawa measure doesn't care that you multiplied omega by -5. So this is independent of the choice of omega. Okay, so what's the point, or what does this buy you? Well, remember, you had this formula. The mass of Q, well, up to some power of 2, which I'm going to ignore, is given by the measure of SOQ Q divided SOQ of the Adels mod Q times the measure of SOQ of Z hat cross R. And here I was allowed to use any Haar measure on the group SOQ of the Adels. Let's use the one I just sketched the construction of, the Tamagawa measure. And the virtue of this is now it makes sense to talk about the numerator and denominator independently of one another. So the denominator is actually something that you can explicitly evaluate. So SOQ of Z hat cross R, this is literally a Cartesian product of SOQ of R, this compact Lie group that I mentioned earlier, times the product over all primes P of SOQ of ZP. Now, I didn't quite say what I meant when I meant define Tamagawa measure to be this product of measures on the individual factors. What it means is that if you want to feed into it something like this, that's literally a Cartesian product of subsets of the particular factors, then you just, the Tamagawa measure of this is essentially by definition obtained by taking mu omega r, evaluating it on SOQ of the real numbers, times a product over all primes P of mu omega QP, evaluated on SOQ ZP. Okay, so if you pick your favorite differential form omega, this is something that you can now try to compute, right? So this first factor, you're trying to measure the volume of this group of rotations in Euclidean space. And you can imagine that if you try to compute that volume, you're going to get something that involves volumes of spheres. Because the orthogonal group is some kind of twisted product of a bunch of spheres. On the other hand, this product over P of the p-adic volumes of these groups SOQ, ZP, essentially what you're doing is for each prime P, you're writing down some kind of counting problem, and you're taking the solutions to all those counting problems and multiplying them all together. So that's something that you might expect is going to have to do with values of the Riemann zeta function, something with an Euler product expansion. So in fact, if you look back at the Siegel mass formula, as I stated it for you earlier, all of the complications that appear on the right-hand side of the Siegel mass formula come from evaluating the denominator in this expression. And you can get a much cleaner statement of the mass formula if you just focus on the numerator. So let me call this, again, the mass formula, but now the Tamagawa-Vey formulation. The Tamagawa-Vey version is that if you take the Tamagawa measure of SOQ of the Adels mod SOQ of the rational numbers, that this is equal to 2. Now, there's a lot of reasons that you might prefer this statement. First, it's easier to remember. Also, I told you earlier I didn't want to state the mass formula in full generality because it was complicated. So I stated it for you here just in the unimodular case. But actually, in the Tamagawa-Vey formulation, it's not more complicated in the non-unimodular case. This formula is good for any quadratic form over the integers, unimodular or not. It's also good for quadratic forms which are not positive definite, as long as the number of variables is at least 3. But you might still think that there's something a little arbitrary here. Where did this number 2 come from? Well, the number 2, it turns out, comes from the fact that the special orthogonal group is not simply connected. So as I mentioned earlier, this algebraic group SOQ, it's not simply connected. It has a simply connected double cover, which is called the spin group of Q. And you can run a similar story for the spin group. So you can take spin Q and evaluate it on the adels. That's a locally compact group with a canonical measure. It has a discrete subgroup given by spin Q of the rational numbers. And then you can ask what's the Tamagawa measure of this quotient. And it turns out this is equal to 1. And this is, let's say, an equivalent formulation of the mass formula. So it's equivalent in the sense that the statement that I made over there and this statement, you can prove either of them from the other more easily than you can prove either of them individually. Though it's not obvious. It should not be obvious that these two formulas are equivalent to each other. Okay, so motivated by this and many other examples, they made the following conjecture. That this should happen for any simply connected algebraic group. So let G be a simply connected semi-simple algebraic group over Q. Is that my time? No. Let G be a simply connected semi-simple algebraic group over the rational numbers. So then you can take the adelic points of G of the adels. This is a locally compact group. The construction of Tamagawa measure makes sense in this setting. So there's a canonical measure on this locally compact group. And there's this discrete subgroup, which is G of Q. And the conjecture is that in this situation, the measure of that quotient space is always equal to 1. So this measure has a name. This is what's called the Tamagawa number of G. So the conjecture in this terminology is that whenever your group is simply connected and semi-simple, the Tamagawa number is equal to 1. So this conjecture is now a theorem. So it was proved by Weil in many cases. It was proved by Langlands whenever G is a split group, by a student Lai whenever G is a quasi-split group, and by Kottwitz in general. Under the assumption that G satisfies the Hasse principle, which was at the time not known when G was a form of E8, but was later proven by Chernusov. So what I would like to talk about for the rest of the week is the function field analog of Weil's conjecture. So many, many questions in number theory you can ask that make sense for number fields, fields that are finite extensions of Q, also make sense over function fields, meaning fields that are finite extensions of fp adjoin t for some indeterminate t. And the typical behavior is that the questions that you ask about function fields, if not necessarily easy, are at least easier than the questions about number fields, because function fields have a strong connection with algebraic geometry that number fields lack. So this was sort of an exception to that, in that it was a statement which was known for number fields before it was known for function fields. And so what I would like to do is sketch for you some of the ideas that go into a proof of the function field analog of Weil's conjecture, making contact with some recent ideas in algebraic topology. So I guess we will resume in 5 hours, something like that. Thank you very much.
Okay, maybe have 1 or 2 minutes for questions.